Presentations by Dr. Philippe Sierra and Dr. Donald Ingram. The topics are going to be GeroScience, the ultimate preventative approach to chronic diseases, and the serious search for the anti-aging pill. Following their individual presentations, there'll be some Q&A led by Dr. Dan O'Connor, and there'll also be a reception in the same room, so please stick around. This presentation today is the end of what has been 10 lectures and performances and presentations that we've put together this spring that we've dubbed the Innovation Series. And the idea behind the Innovation Series is that art builds a bridge to widely different disciplines, and the kind of dialogue that gets generated with these interactions really contribute to student success. All of these programs are based on an Alzheimer's themed video installation that the museum has called Janet Biggs' Echo of the Unknown, and that show runs through this week, I think through March 21st. And all of the programs are also the product of the work of a steering committee made up of more than 20 faculty and staff and community partners here at the university and in Houston. I thought it's fitting, since this is the end of the lecture series, to give you some idea about how broad these topics have run. And also we have a couple of presenters from the series in the audience today, so I wanted to make sure that we acknowledged them. We began with Jason Erickson from the College of Pharmacy talking about fit body, fit mind, the surprising science of exercise and Alzheimer's disease. We have Larry Shee, who's also here today. He talked about smart software applications for dementia and Alzheimer's patients and caregivers. We brought in Dr. David McLean, who's a graduate of the Creative Writing program here at UH. Had a great discussion, a panel discussion on memory and identity. We brought in Lisa Genova, the author of Still Alice, and had a great discussion on early stages of Alzheimer's. Dr. Jose Luis Contreras Vidal from the engineering department was here talking about your brain on art. Dr. William Winslade from the law school here talked about legal and ethical issues in later onset dementia and Alzheimer's. We brought in, we had dance faculty, Becky Valls, and paired with Dr. Contreras Vidal, did this fabulous demonstration of a dancer wearing an EEG cap and having her brain waves projected on her and the wall behind her as she performed, kind of an investigation of neuroaesthetics. We brought in, through the School of Music, Corrine Tout, who's one of the leaders in neurologic music therapy. And just last week we had History Department professor and Honors College, in the Honors College, Dr. Robert Zaretsky, who had a great talk about Diderot and D'Alembert's collaborative translation project of Francis Bacon's Encyclopedia, which really is about, the encyclopedia is about how all the world is connected, and that's really what this series is about how all the world is connected. Our community partners for the series have been the Alzheimer's Association of Houston and Southeast Texas, the Alzheimer's Disease and Memory Disorder Center at the Baylor College of Medicine, and the Nance National Alzheimer's Center at Houston Methodist Hospital. The partners for today's presentation are the university's Division of Research, the Alzheimer's Disease and Memory Disorder Center at Baylor, UTMB Seeley Center on Aging, and the students that you saw collecting names and directing you as you entered the building are all from the hospitality program and the Conrad College here on campus. To assist me in introducing our two speakers, I'd like to ask Dan O'Connor to come in. So please give him a warm welcome. So Dan. Yeah.
Thank you. It's not often you get applause for just walking to the microphone. I'm here to introduce our two speakers, and it is my great pleasure to do so. I'm an associate professor in health and human performance and the interim director of the Texas Obesity Research Center here on campus. So our first speaker is Dr. Philippe Sierra. He's the director of the Division of Aging Biology at the National Institutes of Aging at NIH. His background is he's trained in biochemistry in his native Chile. He has a PhD in biochemistry and molecular biology from University of Florida. He did a postdoc at the University of Geneva in Switzerland and then worked with Nestle in Switzerland before becoming an assistant professor at the Medical College of Pennsylvania and then an associate professor in the Lincano Institute for Medical Research in Pennsylvania. But then he moved to NIA after completing all of that academic work to continue his research, and he's been there for 12 years. He's the founder and coordinator of the Trans NIH GeroScience Interest Group, also in his portfolio in his spare time. The Nathan Schock Centers for Excellence in Basics Biology of Aging, and the Training Grant Program at NIA. So please join me in welcoming Dr. Sierra.
All right. So thanks for the invitation and for being here. It's a big pleasure. Although I have to say right away that I don't care about Alzheimer's. Okay, I don't care about the diseases of aging. I care about aging. Okay, and I'll try to make that distinction clear for you in my talk. So basically, I will be talking about this. Let me see. Yeah, this GeroScience concept that we have been developing over the last few years. And I will start with some very simple statements that I think are difficult to argue with them. First of all, that the goal of biomedical research is to increase the quality of human life. You might work in worms, you might work in flies, whatever. But your goal actually is to increase the quality, not the quantity, but the quality of human life. I think that's very straight. The main limitation to achieving that goal of having high quality of human life is the chronic diseases of the elderly. We have conquered all the other diseases, the childhood diseases. The main issue that we have right now is the chronic diseases of the elderly. And therefore, aging biology must be the major risk factor for most of these diseases. I will work a little bit on this because it's not so obvious that is the case. So let me just give you some examples. So what are the major elements that affect your health? We're always talking about the genes and environment. So it's your genes, your environment, how much you eat, how much you exercise, this and that, and your genes, your parents, whatever, that gives you your chances of getting any given disease. So it's the intersection between genes and environments that is your risk factor. But that is true only when you're talking about the young. In the old, you have the genes and environment. In fact, the genes have not changed from when you were born. The environment is something that you can modify, and that's an important thing. But on top of that, you have aging. The process of aging that, again, affects the way you have disease risk. And that risk of aging gets bigger and bigger as time passes by. So at the end, this is your risk when you're old compared to when you're young. And that explains why the curves of mortality all have this shape. It's a very funny shape that after 65, everything shoots up, while the diseases are very minor when you're young. So let me give you now a more specific example. So the major killer in our society is heart disease. Okay? So what are the major risk factors of heart disease? We all know it's cholesterol, obesity, blood pressure, and the usual suspects: smoking, exercise, diet. You can go to the doctor because you hurt your toe, and they're going to tell you those things, right? For everything. The reason, in my opinion, but I have no data to prove that, is that these things affect the process of aging. And that's why they're important for all diseases. But these are the usual suspects, okay, the ones we worry about. So let me do a try here. So this is me and my daughter, okay? Let's assume that I'm a very, very bad parent, and I take her out to eat junk food 3 times a day for 5 years. I'm not a bad parent. I would not do that. Okay, but let's assume. What would happen to her? What would happen is that her risk of cardiovascular disease would increase 3, 4, 5-fold enormously because of the bad cholesterol, the obesity, and so on. What will happen to me, however, is a little different. Why is that? It's the same cholesterol. It's the same bad diet. Why do I die? It's because I'm old. That's simple, right? So the major risk factor for cardiovascular disease is not cholesterol, it's not obesity, it's aging. That's simple. I can tell you the same story for cancer, I can tell you the same story for a lot of other diseases. The major risk factor for all those chronic diseases is aging itself. Okay, so what I've told you so far is that aging is the major risk factor for chronic diseases. Duh, we knew that. We already knew that. As you get old, you get more chances of getting chronic diseases. Yeah, of course, we know that. We also know that, unfortunately, I cannot change my age. It's in my birth certificate, it's in my driver's license. I can lie about it, but I cannot change it, okay? And that's where you're wrong. Because physiological aging is plastic. Chronological aging is not. I'm 62, and I will be 62 until October 3rd, the day before my birthday when I will be 63. That's it. I cannot change that. Physiological age, we're known forever. You can change by exercise, by diet, by all of those things. You have seen 70-year-olds that are running around, and other 70-year-olds that are like this. They're the same chronological age, different physiological age, okay? And that's the point I'm trying to make. So what happens is plastic, and in the lab, in mice and other animals, we can change this, for example, by dietary restriction. You can make an animal eat 40% less, and it lives 40% more. Sounds great, except we won't do it, okay? We can do it genetically. We have at least 700 genes that can make a worm, for example, live longer. Or we can do it with drugs. And that's something that's very new, that we can do it with drugs. We can take a pill that makes you live longer if you're a mouse, okay? Very important, if you're a mouse. But the important thing is, as I said at the beginning, our goal is not to live longer, it's to live better. So the bottom line actually is health span, which is the period of your life that you're in good health, is also improved. So let me just show you, just to give you an example, we have at the NIA the interventions testing program, in which 5 out of the 16 compounds we have tested so far have given a positive result in at least one sex of the animals, okay? So that's very promising. With rapamycin here, which is a most studied, we tried with 3 different doses, and there was a dose-dependent response in longevity. But the important thing is about the health. We have tried rapamycin in a lot of animal models of different diseases, and they are better in terms of the diseases. And in here, I don't have to tell you much. You can see that these mice are running around. They're treated with rapamycin. The controls are not really running around. These mice are 38 months old. That's the equivalent of a centenarian for humans, okay? So no surprise that these guys are not moving much. They're centenarians. But look at these guys, they're the same age. They're in better health, okay? I can give 2 lectures on rapamycin effects on health, but I won't. So in summary, we can intervene. Okay, that's good. We can affect both the length and the quality of aging, of quality of life. Should we? And because there's a lot of philosophical issues in there as well. However, I have to say that all biomedical research tends to do the same. When you're working on cancer, you're trying to increase the lifespan and the health span of those patients. Well, I don't work on cancer. I don't work on Alzheimer's. I work on aging. I'm not trying to increase lifespan or health span in those patients. I'm trying to increase it in all of us, okay? So what I always say is that if you're not studying aging, you have been misled because you're not studying the main thing, okay? So I would say that not only we should, but in fact, it would be responsible not to address the major risk factor for most chronic diseases. We have to do it. So where do we start? So many chronic diseases are studied individually. You have a person who studies cancer. Oh, I'm a cancer biologist. I'm an Alzheimer's disease person. I'm a vascular disease person. Not only that, they even have their own institutes at the NIH. So you have a cancer institute, you have an HBI, you have an IA for Alzheimer's, you have your own institute. What? Does that make sense? If the major risk factor is the biology of aging, and these are the type of things that we focus on within the biology of aging. So there's only one division within one institute, the one that I ran, that studies the biology of aging. And there's 27 institutes studying these different diseases. There's a different disparity there. But what I'm trying to do, actually, is to combine the two. How is the biology of aging affecting the biology of disease? And that's where the concept of GeroScience came in. So it's a convergence between biology of aging and biology of disease. So the definition of GeroScience, you can see this in Wikipedia, and it's correct because I put it there. GeroScience is an interdisciplinary field that aims to understand the relationship between aging and age-related diseases. It's not rocket science. Oops, I shouldn't say that in Houston. Okay. It's not a very unique idea. It's very obvious that these two things are related. So what is our hypothesis? We think that aging is at the core of all of these chronic diseases that affect the elderly population. And therefore, if we can, as we do it in mice, if we can reduce the aging process, we will reduce all the diseases. That is the hypothesis. It remains to be proven. In our animal models, it happens. In humans, we don't know. So this leads to the issue of comorbidities, because as you get old, you don't get one disease, you get several. So you get comorbidities, you get multiple diseases. So our model so far is we try to cure one disease at a time. And I'm not sure, in young people, by all means, that's a good idea. So if you're young and very fat, as you can see, you might get a disease, you might get cancer. Okay, by all means, let's cure it. You might leave you a sequela, okay, and it does. But by all means, try to fix it. That person might get a second disease eventually. We can cure it too. Great, let's do it. In the old individual, the situation is a little bit different. They don't get one at a time. They get several. And if we cure one, which, by the way, we never cure these diseases. We treat them, we manage them, we don't cure them. What happens is we're increasing the length of time that this person will have to live with the other two. So we're increasing his or her lifespan, but not her health span. In fact, we're making that person live in terrible condition for longer. Is that a good idea? Maybe yes, maybe no. So I think we need to break this war on disease X model. So we have a war on cancer. We have a war on Alzheimer's. We have a war on disease. We are very good at declaring war on these diseases. It works for some of them. We declared war on polio a long time ago, and we won. We declared war on HIV, and we won. Let's try to win the war on cancer or on Alzheimer's. It won't happen, because these are much more complex diseases that are not one etiological origin. They're much more complex. We can't address one disease at a time. We have to address what's behind all of them, which is the process of aging. So instead of having these silos where each disease is studied separately, we need to, Jay Olshansky says it very well in here, we need to have a more comprehensive approach to the whole thing. So let me just give you, again, an example of that. So because of our genes and environment, we each have, on each one of our functional domains, say the immune system, the cognitive function, etc., we are born with a certain capacity, and eventually it goes down. The important thing is it goes down for everybody. That's the process of aging. That's not disease. It goes down for everybody. It doesn't always cause disease, but it does go down. And what happens is that you die when the first one of these goes down so much that it's incompatible with life. So in this particular example, we focus on the cause of death, and this person died of diabetes, because that's the system that that person had weakest. Others will have others, because these lengths are different for each person. But that person died of diabetes, but I don't work on the National Institute of Death. I work at the National Institute of Health. I don't work on the National Institute of Diseases either. I work in the National Institute of Health. Where is health in here? On the cause of death? I don't think so. What's important to me is that this person, yes, died of diabetes. What's important to me is what it had together with diabetes. So all of these red things, it has sarcopenia, dementia, and cardiovascular disease at the same time. That was the health of the person. This is the death, this is the health. Okay? I think we need to take all of that into consideration when we're doing our studies. Can we translate this into humans? It's very important to realize that mice are not little furry humans. They have different physiology. We have cured diseases many, many times. We have never cured diseases, really. We have cured bad models of those diseases. So are our models any good? So our idea is we go from mice, usually mice, this is what we use the most, and we want to translate them to humans. We usually study, say, cancer, cardiovascular disease, Alzheimer's. We study in young mice. Then we try to translate that into old humans, and we're surprised that it doesn't work. You're comparing apples and oranges. You're doing something really wrong that you were taught about your first year of science training. Don't change two variables at the same time. Well, you're changing the age and the species to big variables. So I would say at least we study old mice. It's a little more of a chance that it will translate. It's not proven, but it's a possibility. But there's another thing, that these models of aging are not really, these models of disease are not really disease. They're caricatures of the disease. You don't have a model of Alzheimer's. You have a model of overexpression of APP, right? You don't have a model of cardiovascular disease. You have a model of decreased ApoE and high-fat diet. It's not really the right models that we're using. So what I'm trying to do actually at the NIH is trying to convince people to at least age their models so that at least one of the variables is taken care of, okay? There's other things like the genetic heterogeneity. You know, most of the research is done on young black 6 male mice. It's one animal, genetically, right? It's like if all we know about biomedicine was known about you, but not you. What's the sense of that? In aging research, we have some advantages. First of all, before we get to the mouse, we get to test rapamycin in mice after we already know that it works in all of these species. Because experiments in aging, of course, take a long time and they're expensive. So we don't go directly into the mouse. We try first in other species. So by the time we get to the mouse, we know that rapamycin, for example, works to extend lifespan and health span all the way from yeast to mouse. Now, what we want to do is, and we're starting this, we're starting in dogs and in monkeys. If it works on those, then we can go to humans. So that's an advantage that we have over the disease-oriented research. But we have a clear disadvantage in that we normally, our classical approach is to measure lifespan. So this is an experiment on dwarf mice that are defective in IGF-1 signaling. They live longer. Yeah, but it takes forever to do it. And needless to say, if we're going to be working with lifespan, it's not going to work very well in humans. You're not going to do a lifespan study in humans. Okay? That's kind of complicated. So we need to develop proxies. ways in which we can measure whether our treatments will help the health of the elderly, but without measuring lifespan itself. So what we have been proposing is to use resilience. So what is this? And I'm not talking about resilience at the psychological level. I'm talking about cellular autonomous resilience. So the idea is you give a stress, for example, oxidative stress or any other thing, a cold, not a cold like in, but being cold, being cold, being hot, things that the whole organism has to respond, and it's independent of the HPA axis. It's not whether you feel like it's cold. No, you are cold. Okay, your cells have to respond to that. So the idea is you give a test, you intervene, and then you stress again. And you see, did it improve? Did the intervention improve your resistance to stress? Limitation is that we have to show that this resilience does have an effect downstream into longevity and health in humans. Once we do that, we can use this as a surrogate for what we really want. So there is a proof of principle that was published actually exactly on Christmas Day last year by John Manick. She took 218 subjects, humans, old humans, 65 and older, and gave them rapamycin for 3 doses for 6 weeks, different doses and so on. Then gave them a washout for 2 weeks, very important, so the individuals were not having rapamycin in their body when the test was done. And then the test was something that they were going to get anyway, an influenza vaccine. And the question is, did this treatment with rapamycin improve the response to influenza? And the answer was yes, it did. 20% increase overall in the response, in other words, the antibody titers that were obtained after the influenza. As you know, old people don't react very well with, to vaccines. Okay, there's a problem with that. We always tell the old people that they have to get vaccinated. Yes, they do. Yet we know that the response is much lower, but it's not zero. So that's why we always say that they should. But there was a 20% overall increase in the response. Okay, and interesting, the low dose, because they tried 3 doses, the lowest dose was the most effective, which is kind of nice, you know, from the perspective of pharmacokinetics. So the principle is there. You can test something, a test that measures your resilience, and the intervention does help it. So what do we measure for resilience? So there's a lot of work being done right now on measuring frailty in mice, how the mice behave as they age, how their physical functions work. But we're actually talking about resilience, the response to a stress. You stress the animal, does it respond well? And if it responds well, I'm going to leave my slides in here so you don't have to take a photo. If you stress the animal, it does better. And if it does better, does that mean that that particular animal that does better than another one, is that animal going to live better and longer? Those are the questions that we need to answer. So we are talking about measures of resilience that are very general, not specific for one system. So that's why I mentioned, for example, the heat and cold, the high-fat diet, which of course is very relevant to Americans, unfortunately. Smoke, toxins, surgery, for example, is something that we all do get. Okay, and then, for example, some humans get elective surgery, even when they're old. And I'm not talking about you know, Botox or things like that. They have a problem with the knee. They have osteoarthritis. They're going to get a knee replacement, but they know they're going to get it. So we could contact them before and say, okay, before you get your operation, let's try this. Okay, those are the type of things that we're talking about that we could do. So, in conclusion, actually the conclusions were from a longer talk. So I haven't separated. So in aging biology, we have many things the major hallmarks that have been identified, which is what allowed us to be successful in 5 out of the 16 things we tried with the mice in the intervention testing program. It's because we pretty much know what we're doing. We know enough about aging to be able to predict what's going to happen. Do we know everything? No, by no means. But we know enough. There's these major hallmarks identified, 6, 8, 9, depends on which paper you read. We need to develop them into biomarkers. In terms of GeroScience, there's 2 concepts that I wanted to leave you. One is that aging is at the heart of chronic diseases. And I don't think that that's saying something new. You knew that. The important thing is that aging is malleable. And it's malleable by simple means such as exercise and diet, but it's also malleable by drugs, by genetics, and other things. And on translation, we have robust fundings, and the field is poised for translation, but we are not quite there yet. We are about to start several trials, actually, and I cannot tell you which ones, but we're about to start several trials in humans to test these concepts with some of the drugs that we have found. It's very exciting. It might not work, okay, but it might work. And we're trying also with dogs. We started a big project on trying to use common house pet dogs for our studies. We're not going to bring them to the lab. Yeah, they're going to live with the people that they always live with, but they share their environment. They share a lot with humans. And if it works in them to increase their health span, even if it doesn't work in humans, that would be a great thing, because everybody loves their dogs. Okay, so if it works in dogs, I think it's going to be a big step forward. Oh yeah, and since this was multidisciplinary, these are my paintings. I paint in my spare time. All right, thank you.
Let me see, I think we're going to, whoops, maybe I'll just sit and do this. I think we can ask questions and then we may come back at the end also and ask, sure, while it's fresh in the mind. So does anyone have any questions to start?
Yes. So, yeah, very, very interesting. So, rapamycin is a drug that was found in the soil of Rapa Nui, which is Easter Island for everybody else, but actually, Rapa Nui is a Chilean island, and I'm Chilean. So I had to say that. And it is used as an immunosuppressant, but it turns out, and this is one interesting thing, it's used for transplant patients. But it has been found recently that it's not really an immunosuppressant. It is an immunosuppressant in young people, but not in old. In the old, it's an immune modulator. It turns out that in the presence of Rapa, the response, say, to a bacterial or a viral infection is actually improved in old mice, not in young. So its role within the immune system changes as the animal ages, which is another important thing. When I was saying about the importance of testing things in old animals and not in young, even if your mouse is a Mickey Mouse, still is important, because the response is different in young than in old. It is 100% change in what it does. Yeah. Questions from the young people? No questions. Gee. Yeah, that's a very important question, actually. Why do we do genetic studies? We're not planning to do genetic engineering on humans, that's for sure, not even in dogs or cats or anything, no. But what it does is that it allows us to identify pathways. So just to give you an idea, I'm keeping with the rapamycin example. So what was found was in yeast. They did a test, they mutagenized the hell out of them, okay, and they looked for yeast that live longer. And some of these yeast that live longer, they were able to identify what gene had been mutated. And the gene that was mutated was this protein called mTOR. In fact, it was an effect of mTOR, a 6 kinase, but you get the idea. So you modify a gene, and that allows you to identify that that pathway is important for the effect that you're looking. Now let's look for molecules that affect that pathway. And in that case, we're lucky because the pathway is called mTOR, which stands for target of rapamycin. So we already had a drug. The drug was there, it was rapamycin. Okay, we tested it. And voila, the animals live longer. So the genetic manipulations are that. They're helping us identify the nodes, the areas where we should concentrate. No, we're not planning to genetically modify anybody. Yeah. Okay, a very complex question. So we have focused most of our research on measuring longevity rather than aging. We know, yeah, it's only time. We know it's a bad measure, but just to explain you a little bit, most of precisely the genetic work was done in C. elegans and Drosophila, these tiny little things. It's very difficult to ask a C. elegans how you're feeling today. So asking for the health part was not easy. But to do the genetic analysis, we need an animal that lived very, very short. Otherwise, it becomes impossible, right? So we focus on longevity with the assumption that if an animal lived longer, it had to be because the health has improved. The opposite is not necessarily true. An animal can live short if you hit them repeatedly in the head. It has nothing to do with aging. So short-lived animals are questionable whether they're help, but long-lived animals are. Okay, so once the first way in which we got an extension of longevity was in 1935, actually, McKay with the dietary restriction. And decades of work on that show that indeed those animals live longer and they are healthier. So that kind of proved that logical path was correct. However, it has to be tested at every point. So how do we measure aging? We're measuring what we call health span, but we don't agree about what health span means. If it helps you not lose your hair, that's not important, right? But if it helps you with your cardiovascular, it is important. So different people, unfortunately, use different parameters in there, and it's difficult. Yes. No, because not everybody gets disease. Everybody gets aging. Yes, very, very good point. So if you take an animal or a human, say a human that dies at 80 years old, usually you can tell what it died of because it had spent millions of dollars in treating that disease. If you take a centenarian, usually you cannot tell what they die of. Why? Because they didn't have any disease. They kind of collapsed, and we don't know why. I would say that that person died because of multiple failure in all of these systems, but none of them a failure bad enough to be called a disease. So the pathologist cannot say this person died of diabetes. They cannot say in those individuals. And the same is true in calorie restricted mice, for example. We cannot say in many cases what they die of. When all the what are shed off? The telomeres. That is one hypothesis. There is a good correlation between telomere length and age, telomere length and stress, telomere length and some diseases. Those are correlations. Cause effect, I have not seen any.
let's move to the next speaker, and I think we can, at the end, we'll have individual questions, and then maybe come back to some of these issues. Thank you for that talk, very interesting. Our next speaker is Dr. Don Ingram from Pennington Biomedical Research Center. He joined Pennington in 2006. He's a professor in the Nutritional Neuroscience and Aging Laboratory. He joined Pennington after retiring from the National Institute on Aging at NIH, where he had been since 1980, most recently as chief of the Laboratory of Experimental Gerontology. His undergraduate degrees in biology or psychology from Louisiana State University, and he has a doctorate in psychology and gerontology from the University of Georgia. He did a postdoctoral fellowship at the Jackson Laboratory in Maine, and his research is focused on pharmacology.
The symposium. Marianne, thanks so much for your long-term friendship and collegial experiences we've had. Dr. Ottinger, I've worked together for a long time. I haven't been in Houston for some time. I did spend a summer here way back, 1973. I was at Baylor, and I was taking courses in biostatistics, which all the students out there get your training in statistics, all right? It's very, very important. Those little programs you get now are not good enough. You've got to have a foundation, an understanding of statistics. All right, so I was instructed to come up with some intriguing title, and I haven't used this one before. So I'll tell you what that context is, and I'll try to explain it. And I want to thank Dr. Sierra for setting this up perfectly. We'd talked about this in advance, and he's really set me up for this lecture, and I'm going to reinforce several points he made, but I won't need to do a lot of explanation. Just want to note my disclosures. Dr. Sierra mentioned GeroScience a lot, and just in fact, we founded a company now over 15 years ago. What happened to the slide advancer? There it is, right in front of me. Oh, okay. Yeah, hello. Yeah, so this one and one recently we've formed. So there are companies involved in this technology, and I'm going to explain a little bit more about that. So here was the first time this title was used in a Scientific American publication back then. Quite controversial in its title. We didn't give it that title. I mean, Scientific American wants a lot of publicity, and our director, scientific director and director, hated this title. They hated it. But they were trying to reinforce, that even in government labs, NIH, scientists are seeking a drug to be able to prolong life and youthful vigor. Studies of calorie restriction are showing the way. So that sums up the whole talk, is that my colleagues and I here, George Roth and Mark Lane, were very immersed in the study of calorie restriction, and Dr. Sierra's already mentioned that paradigm, so I'm going to expound on that. But that comes in the context of, this hype about this whole area. I mean, you can go Google this, and you're going to come up with the history of such claims. You're going to come up with historical treatments to try to slow aging and rejuvenate you. You can find tons of pills out there if you so desire to take them. You can read book after book that claims, how to slow aging, rejuvenate yourself. You can actually go to clinics and get rejuvenation treatments, and so you're not at a loss for hyping this whole aspect. Was one of the reasons that, among many, that our director and scientific director just hated that title. That, well, we may be serious, but anti-aging. They even hate the word anti-aging because it sounds like you don't like old people, and so that's a problem. But we've arrived, and this, if you note here, is the, I can't see that date up there. I'll give it to you. It's February 23rd, to March 2nd, 2015, cover of Time. If you haven't, who's seen this title? Okay, yeah, so it's very interesting and mentions a lot of work that Dr. Sierra's office is supporting. So this baby could live to be 142 years old. Is that really feasible? Is that really scientifically sound statement here, or is it again just more hype? Well, what are the processes of aging? Again, thanks to Dr. Sierra, we know that there are many, that it's very complicated, and so that even adds to the, it adds to the skepticism about you could do anything. I mean, here you have all of these different processes that are interacting and converging to produce the phenomena of aging. So how is it that you could think about an intervention that might affect that susceptibility to chronic disease when there's so many involved? You know, are you going to have a drug towards telomere shortening? We've already mentioned that. DNA damage. How do you get to a locus of intervention that would have this broad effects that we associate with the many causes of aging? So the real question is, can aging be manipulated? Well, this gives you an example that sort of indicates it might, but it doesn't give you the complete picture. So here we have a survival curve, and Dr. Sierra's already presented that as sort of a model of how we measure aging, the demographic of it, if you will, mortality experience. And here in 1901 you see the experience, a lot of infant mortality kind of leveled off and stretched out this fashion. So in 2003, you see there's substantial progress already made. Now that was due primarily to major improvements in public health and in the treatment of specific infectious diseases. So drugs were involved, and even in chronic diseases. So there were improvements in the treatment of heart disease, there were improvements in the treatment of cancer that added to this increase in the median lifespan. But here we see down at the tip of this curve that we hadn't much affected that. And the end of that curve is anchored by this woman on the screen, Ms. Clement of France, who died at the age of just over 122 years of age back in 1997. So she anchors the end of that curve. But what we're talking about is, can we push that? We push it out to where it's almost squared up. So, you know, we've removed a lot of diseases here that kill us before we reach a median age. But can we move that curve to the right? And that includes the median lifespan, but also the maximum lifespan. And so gerontologists has taken this as the most substantial data, the most substantial conclusion that we have manipulated aging to move that curve to the right. So that's what Dr. Sierra was emphasizing. But as he also mentioned, it's not just the lifespan that is intended to be affected here, it is also the health span. So the prima facie assumption is that if we do this, we're going to increase, yes, how long you live, but also how healthy you are, how mobile you are, as he showed you in the mice treated with rapamycin. So here's the survival curve. It's shown many thousands of times now. Colleagues Rick Weindruck and Roy Wofford, who were at UCLA. And we have here, you see, we already squared off this survival curve with these long-lived hybrid mice. They're living quite a nice life there, out to 40 months of age. But here are a group of mice, genetically identical, the same environment. They're given the diet 40% less. So he said this phenomenon has been known for decades, dating back to McKay's lab at Cornell University. But see, we moved that median lifespan and that maximum lifespan. So this was taken as the best evidence that with all the complexity of aging, all these many processes, the simple removal of food could have such profound effects. And let me tell you, the first time I put my eyes on this set of animals, it happened to be at the Jackson Laboratory, was my first postdoc, and looked and understood that they were the same animals genetically, and in the same environment, and the difference in their aging was profound. And the video would show their movement as further evidence of that. So very robust effect. There's tens of thousands of rodent studies, similar number of thousands of invertebrate studies that show the robust effects of calorie restriction on lifespan and health span. Some vertebrate studies, including one study in dogs that was done by Purina over a decade ago now. And the question is, does this paradigm of 30 to 40% calorie restriction apply to aging in long-lived primates? And that question is still, in terms of lifespan, debatable. And there are lots of reasons from an evolutionary biology point of view that we could spend time discussing. So I've been involved in a long-term rhesus monkey study, 30% calorie restriction, and we've come to the conclusion that we don't think it's going to increase lifespan in the rhesus monkey. It definitely increases health span, but maybe not lifespan. Another study at the University of Wisconsin has concluded that it does increase lifespan in rhesus monkeys, and also, not surprisingly, health span. Humans will never know, but there have been short-term controlled studies, one done at my institution, Pennington Biomedical Research Center. It's going to be 2 years in normal weight individuals of a 25% calorie restriction. You're going to start to see results coming out of that. Now, we're not going to know whether they're going to live longer, but the measures there are going to be surrogate measures of health, disease risk markers, and they're going to be impacted. And guess what? Not by 25% calorie restriction, because diet studies are so hard to do. And this was one of the best diet studies ever put together. Smartphone feedback technology, dietitians giving you calls on the phone. The average restriction was 15%. But there were still health benefits in normal weight individuals to that. All right. So here are the major features, just to sum up in a few words. But I want to emphasize that it's improved. The maintenance of good performance late in life is also a major feature of this restriction in animal models. But, you know, if we had done the human study 50 years and we had found that humans not only live longer, but live healthier, but also live longer, say by 20 to 30 years. If that study had already been done, you know, we're now, you know, 50 years from now, and you say, okay, am I going to, here's the prescription, eat 30% less than what you're doing now. The question is, could you do it? In a calorie-rich environment like Louisiana, that's a tough one. That's a tough one. So because we're wired to eat, right? And it's just that when we're in calorie-rich environments that we suffer the consequences of having too many calories and when we lower our energy expenditure. So the alternative question that my colleagues and I came up with many years ago now, over 15, can we develop treatments that slow aging by mimicking the beneficial health effects of calorie restriction without requiring a change in eating habits? And we published this paper, it's a first volume, and we tried to get it published in high visibility papers like Science and Nature, and they just didn't like the whole concept. But we got it published in the first volume of this interesting Journal of Anti-Aging Medicine. And here are the features. Mimic certain metabolic effects of CR, activate the stress response pathways, and provide stress protection, because a diet is stressful. And that's good because it activates stress responses. Do not significantly reduce food intake. Now, there are many interventions we could talk about, like appetite suppressants, that would suffice perhaps to produce the effects of calorie restriction. But from a scientific point of view, that would just sort of be difficult to conclude that it was something else other than reducing your caloric intake that was producing, that the drug was actually working to reduce aging. Increase lifespan and health span, including the effects on diseases. All right, so we've published several review articles on this, keeping up with the literature as it has expanded. You can find in the literature, if you go to PubMed and look up calorie restriction mimetics, or you look up diet restriction mimetics, they both refer to the same thing. There's some subtle differences. I won't go into that. But you can find these very useful review articles. And to the major resource of our time, Wikipedia. I got to find out how you wrote that, because I got a couple of articles. You got to know somebody? You got to know somebody. Okay. It's not easy. Who's written a Wikipedia entry? Oh, okay. So he's the only one in the room. Okay. Anyway, so you can find that, and I'm just highlighting. You see some of these that I don't know who the author was. I haven't dwelled into to find out who it was, but there are lots of candidates. I'm going to kind of highlight the ones that you see in yellow. In addition to the belief that maybe it could be done, then there was money put behind this possibility. There are companies formed. Many of these are just small companies, like the one I mentioned, our little company, that are, you know, just virtual companies. But others I'm going to tell you about really grew to the size of significant major pharma. So that was interesting that they started. Now, again, when you go on Google and you do a search, calorie restriction mimetics, you will come up with a dozen possible candidates. Calorie restriction mimetic formula, and here's one I'm going to talk about, but other of these are plant phytochemicals that probably have health benefits. The point is that this formulation has never been evaluated, even in an animal model, much less in some human clinical trial. All right. Here's a question we were confronted with. If you're going to develop a calorie restriction mimetic, do you really need to know the true mechanisms of CR? It'd be good if you did, looking for these mechanisms. And just like all the mechanisms of aging I showed you, well, those are all involved in response to calorie restriction as well. So it's very complicated. But there have been some excellent review articles that have outlined a lot of work which identified these key genetic pathways in these different animal models. We've already talked about this mTOR pathway. I'm going to talk a little bit more about it again. And this is insulin signaling IGF-1-like pathway. has interesting effects in this transcription factor of DAF16 in worms and FOXO in flies and mammals that are important transcription factors for activating a lot of different stress response pathways, including antioxidant defenses. So some of the pathways have been identified through using knockout technology, through transgenic technology. So there are reasonable targets for pharmacologic intervention. And this is the one that Dr. Sierra's already mentioned, with that as its target, and I'm going to cover these other two candidates with a little bit of detail. But there are others. It's a field that's expanding, that there's room for investigation across a broad range of possibilities. So I'm going to mention just briefly these other candidates as well. But here's the example of the company that got a lot of attention from investors, created a real laboratory situation, and then got the notice of even big pharma. So this is called Certrus, and this was headquartered in Cambridge, Mass., founded by David Sinclair, who was a Harvard investigator. I'll tell you the basis of that. But note that the focus here is our drug candidates are designed to mimic certain beneficial effects of calorie restriction without requiring a change in eating habits. So here is the set of genes that began the discovery process in the laboratory of Lynn Garanti at MIT. And this group of young postdocs have just gone on to brilliant careers in gerontology, really focused upon this set of genes called sirtuins. This is SIRT1, SIRT2, SIRT3 has now become the focus of a lot of interest because of its involvement in mitochondrial metabolism, mitochondrial biology. So they set forth on this mission to show that that this gene pathway was very much involved in response to calorie restriction, and therefore very much involved in regulating aging and longevity. And you can see that particularly this first focus was on SIRT1, that it activates all these different kinds of stress responses, and has a broad range of effects. Now, so who's heard of this compound, resveratrol? I'm not going to ask who's taking it, but this got the most. Mm-hmm. Oh, okay, yeah. Yeah, right. Well, you know what he's talking about because it comes from that. Most of it's actually made from Japanese knotwood and not from red grapes on a commercial level. But this interesting phytochemical fell out of a huge screen that was done by Certrus, in which a number of polyphenols fell out. But resveratrol appeared to be the most impressive activator of the SIRT1 gene. That's how they set up an in vitro assay for activating SIRT1, and this one came out as being the most impressive. And again, we're using the brilliant setup that Dr. Sierra's provided. So you test that in invertebrate models. So you're looking at the effect of resveratrol. When you look at the effect of whether when this is SIRT2 is in invertebrate models rather than SIRT1. So this is feeding resveratrol to these invertebrate models, and you got increases. But the big question became moving that on to a vertebrate model. So here was just what's been an incredibly productive partnership between David and a person who was in my lab, Rafael de Cabo, and to propose that we can look at resveratrol in a survival study. Now, that was with black 6 mice and not heterogeneous mice. I'll show you that. And the first foray into this, well, let's stress them by putting them on a high-fat diet. And that turned out to be quite impressive. So here you have mice that are on a control diet and mice that are on a high-fat diet. And here's the high-fat diet with resveratrol. Well, it has no effect on their weight or their body composition. But here's the mortality experience of control mice, and here's the mice on the high-fat diet. So it was very, very toxic high-fat diet in this regards. But those on the same diet with the resveratrol added showed incredible protection against this toxicity. And here's just another example of that in terms of measuring the plasma glucose levels or plasma insulin levels where the high-fat diet drives it up, and the resveratrol protects against it quite impressively. So that was very promising. Now, going forward, as you always have to do, this is now in mice on a normal diet, and you can see that there were 2 concentrations of resveratrol added in the diet. This had been the concentration in the first set of studies. It added a higher concentration. And so now you're all familiar with this mortality curve. You can see that it looks like a hint of increasing median lifespan, but this was not statistically significant, nor was there that effect on the maximum lifespan, so you don't see that push to the right. That would be expected if this were genuinely a calorie restriction mimetic. On the one hand, that's the lifespan effects. On the other hand, they're the health span effects, which were quite impressive. Reduced cataracts, reduced heart pathology, reduced bone aging, and improved coordination. So there was even functional outcomes that were observed from this pharmacologic treatment. And no toxic effects. And it's a very safe drug. All right, but then the ITP intervention testing program has gone on to evaluate resveratrol in many different studies, and the bottom line is in normally fed, control-fed mice, there's just no effect. You just can't see a hint of an effect on lifespan. Now, that doesn't stop people from consuming it. You can buy it just about anywhere now, and there are health benefits to this, I believe. I do not take it personally myself, nor do I recommend anyone do that. But the number of health benefits is widely reported in legitimate scientific literature. All right. Well, it didn't. Also, I want to mention a controversy that started that began to shoot down the whole idea and really take the legs out from this effort at Certris, in that there were papers that began to be published saying that your assay is all wrong. You're using a photophore that's giving you the results you want. And we've used some of your compounds, and they not only don't work in high-fat diets, they kill the mice. So this was quite detrimental, and you can imagine that a few people involved in these studies were beginning to be concerned. So this is the small molecule activators that were generated from the company that were directed towards, resveratrol is hard to protect intellectual property on, so they wanted to create these synthetic compounds. And so here was an article that really put a bomb into the middle of this effort. And you don't need to pay attention to it, but it just said, look, this stuff is, your assay is bogus, and it's not working, it's killing mice. Well, Raphael, again working with David, went on to show in his lab now at the National Institute on Aging, that not only did this CERT 1770 work, it worked even in mice that were on a standard diet. So here's the high-fat diet, which it clearly works on, but here's the control diet, and here's the control diet. Here's the control diet with the 1720 in the red. And you can see it's a modest effect on median lifespan, even little effect on maximum lifespan. Here's the protection of glucose. This is in a standard diet now, so even in a standard diet, it can improve glucose tolerance. So this is a very interesting field if you want to dig deeper into it. Here's a summary. It certainly acts through various signaling pathways. I've just said this one, but this is downstream from AMPK. I'm going to get into in a minute. It has other effects downstream. It does resemble, it provides a transcriptional profile that looks for the world like calorie restriction. It definitely improves insulin sensitivity in these animal models, produces many anti-disease effects, reduces age-related pathology. I've shown you some of that, and does not appear to increase lifespan under normal conditions. But that's for resveratrol. But the CERT 1720 might. Maintains health span, and I mentioned a major refocus now on the whole line of research is on CERT3 activation, mitochondrial-based sirtuin, and also a major focus on a precursor nicotinamide. So that's the current state. And the company has gone on to do clinical trials of this compound. And I'll just summarize quickly. You couldn't look at that in terms of aging, but they focused on persons with diabetes or under stress like cigarette smokers. And you can see that these are just safety trials that showed that the compound was safe. Here's a 28-day trial in smokers. There were significant reductions in serum cholesterol, LDL, and triglycerides, and improved measures of blood flow. So it had that effect in smokers. But their real target was diabetics. assuming they were to get that effect on glucose and insulin that was seen in the mouse studies, again, there were significant effects on blood lipids, reducing those, but no significant effects on glucose insulin parameters. So the research with even these synthetic compounds is still going on. They're focusing on a few specific diseases like lupus, so it's there. Now, moving on to one other target in a drug category, I mentioned this AMPK. You can see that it's situated to affect many different signaling responses. Over here is PGC1 alpha, working on mitochondrial proliferation, P53. So it is sitting there as a sort of a master regulator. And one of the major activators of that pathway is this compound, metformin. This is the most prescribed drug for type 2 diabetes, and its mechanism, it does work through AMPK, but it has multiple mechanisms. Still, how it does what it does, which is to improve insulin sensitivity, is still controversial. All right. Now, studies going back to mouse models and looking at mortality. This were studies published some years ago by Vladimir Anisimov, where this was first proposed out of Russian laboratories. And this is a mouse strain that's very prone to tumors. You can see the control mice here. These are the mice fed metformin in their diet, showing improved survival in this tumor-prone strain. Here are the tumor loads that the mice get on the control diet. And then you see at older ages, they're more protected against tumors from metformin. Now, when I was still at NIA, we followed up with a study we published a couple of years ago, looking at just one dose, which is a fairly high dose, 300 milligram per kilogram. And you just looking at this, you can see that there's just no effects of the metformin on longevity. But a careful follow-up study done, again, in Dr. DeCabo's lab at National Institute on Aging. Here was the dose equivalent to what we were using, we were using 300 milligram per kilogram per day. So here it is 75 milligram per kilogram per day versus 750. So we were using 300. Here's an even higher dose. And you can see in mice on a standard diet that this 1% dose is toxic. And over here, there's a modest but significant effect on median lifespan and maximum lifespan. So again, you cannot escape the dose response of many of these candidate calorie restriction mimetics. Now, other effects of metformin that occurred, that were observed at 0.1%, the lower dose, food intake was actually slightly elevated. And we see over here, this is cataracts were reduced. These are area under the curve for the glucose response and insulin response were lower. That wasn't significantly lower. And even performance on a treadmill, that is, its sort of endurance, was improved. And this is resting expiratory rate. This is energy expenditure was reduced in the mice fed metformin. So a quick summary of that. It acts through CR-like signaling pathways. Calorie restriction activates AMPK, as this does. Resembles a transcriptional profile of CR. I haven't shown you the data. I'm just telling you that. Improves insulin sensitivity. This is the most reliable drug you can get in any animal study or human to do that. It will improve insulin sensitivity. It has many anti-disease effects that have been shown in animal models and does appear to modestly increase lifespan at a low dose. But it maintains health span, motor function, and cognition. So again, a promising candidate. So the other large category of interest, which Dr. Sierra has already explained, was this target here, target of rapamycin. We have calorie restriction operating here, and we saw that mTOR can act downstream of AMPK, metformin acting on that process. And you see he's given a very good explanation of what that drug is and what it does. I just want to embellish that a little bit. When you're calorie deprived, you're going to start burning fats, any fuel you have. So if you're going to burn fats that have been stored up, and also you're going to take whatever garbage you have in the cell, and you're going to start recycling it, the cell is, to produce energy. So this phenomenon called autophagy, literally eating yourself or eating the garbage, is the process that mTOR has a major role in. When it's inhibited, then autophagy is activated, and that's what rapamycin does. Activates a lot of other genes that are involved in inducing this production of autophagosomes, finding the defective proteins, DNA that's out there, RNA, gobbling them up, transporting it over to lysosomes and digesting, and cellular energy is created. And he's already shown you these results that we were worried the intervention testing program was going to last. We needed a hit. And this was the one that provided us the first hit. And interestingly, because of a technical glitch, it wasn't started till late in life. So that's even more important. If you can have an intervention acting later in life rather than having to take it the whole life, that certainly provides a lot more excitement. And this was proposed to the intervention testing program by Dr. Sharp, who's up at the University of Texas Health Science Center, San Antonio. And so then this now has been replicated many times in different animal models, including in mouse models, very impressive, robust effects across males and females. Here's just an invertebrate studies it's been done in. Again, at this point, highly reproducible. But, as he's already mentioned, all is not well in terms of some side effects. There is increased cataract formation. Here's the mice measuring cataracts at the low dose, a middle dose, and high dose. This was the paper it was published in a couple of years ago. Females, males, and in males, testicular degeneration. So, like with any drug study, there could be possible side effects that have to be evaluated. What happens next? Well, here's one study that sort of clarified, this study done in Dr. Anji Bartke's lab. And this was rapamycin done for a specific period of time. In this case, this was rapamycin for 2 weeks, and then control for 20 weeks, and then rapamycin for 20 weeks. And in that sense, also glucose tolerance had been shown to be impaired. And here you see that control mice have better glucose tolerance than rapamycin mice here and here. But if you do the limited presentation, you see that the rapamycin glucose tolerance is improved and the insulin tolerance is improved. So again, dosing, time of dosing, these are all just important parameters we have to go forward. Now, the effects on mTOR have been, there are two components to that protein, mTOR1, mTOR2, and it's thought that the negative effects of rapamycin, the side effects, are more what are called mTOR activated. So there's a lot of effort now all over this country and the world, in fact, trying to modify that molecule to have more effects on mTOR1. So here the summary of that stimulates many signaling pathways of CR. Again, resembles transcriptional profile, has all these effects, including disease effects. It does increase some age-related pathology, as I showed you. Increases lifespan, even begun late in life. Does maintain health span, in fact, despite these negative effects. And I've already mentioned how the further development is focusing on avoiding the effects of inhibiting mTOR2. All right. Now, I just want to turn just to the last part of the talk to a concept that my colleagues and I have focused more on, which is, so you have these interesting pathways that are activated in calorie restriction, and we have now some proof of principle that drugs directed toward these targets can have these beneficial effects like calorie restriction. But many of these targets, we consider downstream. When calorie restriction pathways are activated, I've said there are many pathways. And so our strategy has been maybe we need to target more upstream and have then a broader array of effects. Now here's a drug that Dr. Sierra had in one of his presentations, just a little more description of it. Acarbose, shown here to affect longevity in males, but not in females, but more recent study has shown that it does, again, dose dependent, can have an effect on females. Acarbose is an interesting molecule. It is also, it's used in diabetic treatment, many parts of the world, particularly in Europe. And what it does is to inhibit glucosidase, and so that it prevents some glucose from being absorbed into the circulation. So it's inhibiting the ability of cells to of the body to take up glucose. Here's some effects that showed the HbA1c, which is a measure of the exposure to glucose, was not affected by the acarbose treatment. But over here you can see that, interesting, glucose was actually elevated. This is circulating glucose, which you wouldn't think that would be a good thing to have. But over here, the insulin levels are lower, at least in the males, not in the females, which had the major lifespan effect here. And IGF-1, which is correlated with insulin, is reduced. And calorie restriction lowers levels of IGF-1, at least in lower mammalian models. Okay. All right. So a key strategy that my colleagues and I have focused on is targeting glucose metabolism rather than putting the body on a diet by eating less food. We'd put the cells on a diet by inhibiting its cell's ability to utilize glucose. And the first candidate we had in that paper I showed you that launched this area of research was a well-known compound, 2-deoxy-D-glucose, which the cell sees as glucose. It's transported into a glucose transporter 2, and it starts to be processed. But because of its configuration, it binds up the second step, phosphoglucose isomerase, and then reduces further processing of glucose into ATP. There are many bells and whistles that go off in the cell if this happens, like give me more mitochondria, I need more energy, start burning those fats, start autophagy. So that was a strategy. And you can see in this invertebrate model of a paper published in Michael Risto's lab a couple of years ago that 2DG treated worms, you see that nice shift to the right in the survival curve. Well, this is why you have to do science, and we invested a lot of time and effort in this compound, 2DG. It produced an incredible phenotype of calorie restriction. It reduced body temperature, heart rate, and blood pressure, all of which are seen in calorie-restricted rodents and calorie-restricted monkeys and men, reduced plasma insulin levels, and there was no or modest reduction in plasma glucose levels. We were worried that, like the acarbose, it might elevate glucose. It had no apparent behavioral toxicity, and it provided a wide range of protection. We could inject this very nasty toxin into the brains of rats. They were protected. They could be given ischemic stroke. They were protected. And there were upregulations of some of these protective molecules like heat shock protein 70 and some neurotropic factors like brain-derived neurotropic factor. Other labs showed that that treatment with 2DG would reduce tumor onset and size. Problem was, long-term, it produced cardiac toxicity at the doses we were using. This is the study we published on that a couple of years ago. So that's a disappointment, but it did produce this phenotype. And now there are other candidate glycolytic inhibitors out there. This is the most interesting one. It came out last year, glucosamine. I'm not going to ask who takes that in the room, but I guarantee you there are a couple of people for treatment of their arthritis. Glucosamine can act as a precursor for the production of collagen. That's why it's taken. But it also is an inhibitor of hexokinase, hexokinase being the first step in the glycolytic pathway. So again, going back to Michael Risto's lab, he showed that worms, nematodes treated with glucosamine had reduced glucose oxidation. They had this bump in their survival, shift to the right, and that ATP production was reduced. Now, there's only been one mammal study, and they did this study in mice. But this was very old mice, which again should be impressive if you can get a lifespan bump with that. So there was a shift to the right, a significant shift. Food intake was not affected. Body mass was not affected. Body fat was not affected. Blood glucose was a little bit lowered. And this is impressive, but I have some issues with the data in a sense that this isn't the best survival curve that we would expect from these mice. But it is very promising. Okay, and they thought it worked through increasing amino acid uptake and catabolism. This was the result of a gene array study looking at succinate and these other compounds that indicated amino acid uptake and catabolism was affected. So here was the target of 2DG. Here was the target of glucosamine. Just to wrap up the talk, in my company, GeroScience, which I'm going to devote full-time after July 1, we've been working with a very interesting sugar. It was in partnership with Procter & Gamble. We have tons of dog data, some very promising data on that, which we now have access to after our license agreement was terminated last year. It's a very interesting compound. Just not the compound, just shows that knocking out the hexokinase 2 gene in yeast can have that effect on longevity. So we're moving with this compound, but it's a very expensive compound. It costs tens of thousands of dollars for a gram. But we were lucky to find out several years ago that it occurs in some plants, primrose, alfalfa, but in avocados as well. Unripened avocados contain about 1% mannose, and we've been able, with P&G's help, come up with a method of extracting to enrich that sugar up to about 20-25%, and we have a number of studies which are going to be coming out to support its candidacy as a calorie restriction mimetic. All right, so we had to show some art. So this is sort of the state of art of calorie restriction mimetics. So I need your, how many art students? Okay, so you're going to be the first one to sound out. Like, what is that? Nah? Now, artist? Artist? No art student? Oh, okay. What is it? Close. It's British? It's Monet. Waterloo Bridge. So the point is that this area is still a little bit out of focus. It's only coming in out of the fog, okay? But as Dr. Sierra so brilliantly laid the foundation, I mean, it's the new paradigm. It has to be the new paradigm. Is looking at aging as the cause of chronic disease and trying to intervene in a very serious way. So this idea of a serious search for an anti-aging pill is realistic. That bridge exists, that we can bridge aging and disease and with his brilliant organizational abilities and move forward. CR-mimetic candidates are being examined that stimulate signaling pathways invoked by CR. Many possible targets exist, particularly within energy sensing pathways. I showed you some of those. Given multiple signaling pathways that are involved in CR, we should consider the potential of cocktails. So some of these downstream candidates might be much more effective in cocktail forms. So in conclusion, research focusing on CR-mimetics is creating a new field of investigation and possible interventions to impact healthy aging, but we still have much to do to make real progress. That's the crowd of collaborators that I wouldn't be standing here if it weren't for their incredible help along the way, and I would thank you for your interest and wish you that.
All right, thank you. Very interesting talk. Are there any questions to start off with?
Yeah, they lose. that sugar degrades. The most popular brand of avocado in the supermarket is called a Haas. It has about 1% in its unripened state, and that degrades to less than 0.05% by the time it's ripe.
Yeah.
No, but
Not in guacamole.
that conjures up some distinct commercial opportunities. I have my colleague George, George Roth, who and Marianne knows and Felipe knows, who's very persistent and has an iron stomach. Yeah, he's eating unripened avocados every day. So, yeah.
Yeah.
No, you don't know George. He'll eat anything and wash it down with a beer. It's all right. So again, it was a promissory note on the human calorie restriction studies that are come out. The big study is called Calorie, that is organized by Felipe's colleague Evan Hadley at the National Institute on Aging, and I think it's going to come out in the Journal of Gerontology now. They went through Cell and Nature and, New England Journal, and, it's degraded all the way to, I shouldn't say that because Rafa DeCavo is the editor of Journal. I'm an associate. Aren't you associate editor? So you say degraded. It's lucky to get published in the Journal of Gerontology. But another study that's going to be coming out from Pennington is going to be finally a comparison of a 60% fat diet with a 60% carb diet. Locked in. These young men were locked into that building for like 6 to 8 weeks. Okay, and so everything they ate was known, and he had to spend a lot of time in a metabolic chamber. Okay, so you have this controversy about high carb, high fat. You want to guess which one turned out to be losing body weight and higher level of energy metabolism? You want to guess which one that was? 60% fat. So that's been the controversy out there, and the study. So it's coming out, and it's going to again turn that thing on its head about are carbs the culprit in our obesity epidemic right now? And fat took such a hit, So yes. Yeah, there's no question, and but the dogmatic view, which hasn't been overturned in a good while, was a number of very well controlled animal studies done, is that with exercise you will get that increase in the median lifespan, but it doesn't affect that maximum lifespan, which means it's affecting risk factors for disease, but you're not fundamentally altering the aging process. That's it's still dogma, but hasn't been overturned. So that's the difference. That's why calorie restriction I would have shown a slide like, here's exercise, get the bump in median lifespan, but here's calorie restriction, you get a 30-40% increase in the maximum lifespan. You move that curve entirely to the right. That's been the dogma. Why? And there's a whole interesting lecture that I give now on hormesis. Who's heard of this word? Hormesis, Hormesis. I got an excuse to come back. So it's only a 4-hour drive from Baton Rouge. But anyway, the bottom line is that just euphemistically, what doesn't kill you makes you stronger. A little bit of poison can protect you against a greater amount of poison. Those would be two euphemisms. And the point is that stressors like exercise and like calorie restriction and like a lot of phytochemicals that actually increase stress. We do a lot of work with blueberries, and blueberries are remarkable in terms of health protection of a number of diseases. They will not increase lifespan at the concentrations we've used in animal models. But what's very interesting, and they will, and presumed effect is like reducing oxidative stress. There are a lot of polyphenols in these interesting berries, and they reduce oxidative stress long term. If you feed blueberries for 2 weeks, you get an elevation. 2 days, you get an elevation of oxidative stress. And that's necessary in order to activate the defense against oxidative stress that then provides them the long-term benefits that they have. But if you don't have that initial oxidative stress, you're not likely to get the benefits. I showed you several slides from Dr. Risto's lab, and he's really making a big case for this. 2DG increases oxidative stress short-term. Glucosamine increases oxidative stress short-term. Exercise increases oxidative stress short-term, and Dr. Risto has published a paper where if you give a high level of antioxidant, you will not get adaptation to exercise. Exercise is damaging. It creates breaks in DNA. It creates muscle tears, and you're activating all these repair systems that you get the benefit from. But the difference probably in calorie restriction and exercise long-term may be too much stress. So stress is a U-shaped function. So you may be going over the top with the exercise and not with the calorie restriction. That's a long-winded explanation. I mean, you got epidemiology data now, and I'm carrying around my little accelerometer now. It's called a Misfit. And I'm going to get my 10,000 steps. So walking is certainly beneficial, and it's not going to be that stressful, perhaps. Will it add longevity? I don't know, but it feels good to walk. Well, calorie restriction even works in germ-free animals. But you raise a good point, which is just exploding on the scene in terms of the interaction with any intervention. We've always just taken the gut and the microflora there as just a constant. It's one of the variables we never controlled. And now we know that, particularly when it comes to glucose and insulin regulation, what bacteria exist in the gut are highly important. I mean, it could be, one of the major culprits in our obesity epidemic right now in terms of the gut flora that we have. So calorie restriction does affect that microflora population and moves it towards the more beneficial type of Clostridium and those other, away from Miculitis. Is that the right? Bacteria.
We can have general questions for a couple minutes. I think you had a question?
All this mechanistic that there's all, drugs and stuff working in your psychology also. So there's not the depression that's the robust mood is what you're talking about. And you know that hormones can be by psychology.
Yeah. I think your criticism is right on, and sure. I mean, but just back in the fog of that bridge in London, Monet, that's where we are. And so the psychological elements of that, and like we just mentioned how gut flora have come in as another variable now, and that was just ignored for decades. And now we know it's a really critical player. And you're saying, well, we already know that brain chemistry is a critical player, but it's still just in that fog as it emerges. And
I'm talking about whole system chemistry, not just, because the brain is a valuable place there to stay. The chemicals go throughout.
Sure.
Right? So if you have, a very wonderful, I miss the dance,
Yeah.
And everything that goes
Yeah.
on and whatever.
Mhm. I'll give you just one example of, because one of our earliest studies when I first got to National Institute on Aging with a colleague I mentioned to you, Dr. Roth, we looked at dopamine system in calorie-restricted rats. Now, dopamine is critical not only to motor function but also to affect. I mean, it's why cocaine addicts take cocaine, because it helps with feelings of well-being and issues of depression. So long-term rats on long-term calorie restriction had their synapses that released dopamine. In other words, we could stimulate them to release dopamine. They would release more dopamine. The receptors for the dopamine that went down with aging in various parts of the brain were maintained at higher levels. So that dopaminergic system was affected. And then when you looked at the rats, and one of the tests we have is just, put them out in a strange environment, and how much are they going to explore? Just move around. And it's called an open field, but it's basically a measure of exploratory activity in a context of novelty. Well, older rats, young rats, just like these guys scramble over here to the student union, they will walk around and just are very curious and looking at this and looking at that. Older rats don't tend to do that. There may be lots of good survival reasons why not to do that, But the older rats won't do that. Well, the calorie-restricted rats and the rapamycin-treated mice, they were moving around more and exploring.
Lab rats or what? Forest. No, it's all lab rats.
Right.
Well, that's. I mean, we don't work with forest rats. The closest we do some work with wild-caught mice, and they behave separate, different. Like for caloric restriction, they behave different. But for example, the work of the intervention testing program that both of us mentioned, that is done not with wild-type mice, but it's done with a genetically heterogeneous population of mice, which has 4 founders. So it's a limited genetic representation, but it's at least better than a single lab mouse. Correct. And the psychological things, of course, there. In fact, when people ask me, if just like Don said, that he doesn't take resveratrol or any of those things, neither do I. But people always ask me, what do you take? And I don't take anything. I laugh a lot. Because that's what you should do.
Yeah, he uses his brain to paint. Yeah.
Yeah, and that's the same thing with the dogs in their home environment. If there are people who are stressed, like, I have animals and they pick up on my stress.
Oh, yeah.
So there's,
That is the idea of going to the dogs, indeed. Yeah, to take all of those, even if we don't understand them, to take all those variables into account.
The other problem I have with this is, not a problem, question, is that the longevity of the drug studies, because you're talking about aging and you're using older mice who are, you're going to die, sooner than later, and your drugs, how long can, the person take it anyway, if it got to,
I don't see
He
the
doesn't take
question.
any things, but I take drugs every day because I'm unfortunately got genes of metabolic syndrome. So I mean, I take ACE inhibitor, that's for blood pressure, and I take metformin to control my glucose, and I'm just stuck with that.
right, but I'm thinking like the dopamine again, and that's how it, the system gets, that needs more dopamine, and more dopamine, and more dopamine.
Oh, I
There's a
see.
diminishing effect.
Yes,
Yeah.
yes,
Right.
that's, yeah.
So how are you going to study that on aging? That's
For the moment, we're not. Again, I think it comes back to the good bridge. There are some things that we know are there, but we can't address them yet. So we need to get a clearer picture before we tackle them. That's being aware of them is all we can do at some point with some of the things. Or keep painting and laughing. I would say even if it doesn't work, that's fine. I
Yes,
won't live
please.
longer, but I will be happy.
Yeah. Yes, please.
I don't think we can say that for humans. There's not enough data to know because maximal lifespan is a complex thing. What is maximal lifespan? So I don't think we can say that in humans. In our animal models, with caloric restriction and with some of the mimetics, yes, we do increase the maximal lifespan too. So in animal models, we can do it. In humans, I don't think we can answer. We have increased the median primarily, yes. But that's because the increase in lifespan that we have done during the last 100 years has been primarily by addressing the diseases of the young. We have conquered a lot of diseases of the young. People don't die on childbirth or either the mother or the child. Those things used to kill a lot of people, and now they don't. So indeed, we're not increasing the maximal lifespan because the things that have helped us move that curve to the right, we're not addressing aging. They were addressing specific diseases. So indeed, those changes have not led to an increase in maxima. Well, if you're looking at the statistics of mortality, yes, you do get into the statistics. You die young. Right, but that's exactly what I'm saying. To to measure maximal lifespan in humans, you need to measure it in billions of people who are very well characterized, and we don't have that.
Interesting demography going on now is that virtually in every country, Western country, that, you know, I showed you Madame Clément, who lived 122 years in France, but in every country with the exception of France, because she set the record, but that person who's lived the longest in that country just keeps going up,
Actually,
in
the data
every
is for
country.
is for mean. The data is for mean.
For men,
Not,
okay, no,
not
okay.
for mean lifespan,
okay,
not
okay.
for maximal.
Uh-huh.
For maximal, for one thing, I mean, you mentioned Madame Calmont. Well, she's an N of 1 in the human
Yeah,
population.
I'm talking about ends of one, like in every country. If you say, like,
Yeah,
let's say in
I
Belgium, the
understand,
oldest
yeah.
living person was 106. Well, now
I
they just
have-
got a new record, 107.
Yeah, I have not
And
seen that. But again, you're talking about a record. A record cannot go down. A record, by definition, has to go up, right? So some people don't measure the maximal, the one person, but what's the probability that 10%? When does the last 10% die? And things like that. But again, there's not enough data that's reliable to be able to say.
The debate is more about whether or not our bodies wear out. In other words, is there any way to estimate at what point we just wear out? Not the disease, not the maybe, you know, the telomeres or too short. Do you have any idea of what that maximum life?
No, because we don't know exactly what wears out, and it's important. So maybe we can replace the telomeres, get cancer, but maybe you won't get cancer. But is that what's important? We don't know. Right. But that's, again, it's an N of 1. So the equivalent of Molly has been done several times. In fact, my old boss, Vince Cristofalo, did it with cows. Those did not live shorter. So it was an N of 1. She died young. Okay.